Hello dear students, I welcome you back again to this short lecture series, and we will continue what we have been studying so far. So we'll just go to this slide. Okay, so we were looking at the sign conventions. So I was telling you what the sign conventions, what are the various sign conventions. So for studying stress transformations, we'll be using these sign conventions, and the sign conventions are as follows. So as far as the normal stress is concerned, for normal stresses, the sign convention for tensile stresses is positive, means the tensile stresses are positive. So in this case, sigma x is positive because it is tensile on this face. It is trying to pull this body apart. And similarly, sigma y is also positive because it is also tensile. So tension or tensile stresses are positive, compression or compressive stresses are negative. Next is the sign convention for shear stress. Now the sign convention for shear stress is a little bit tricky. Uh, we define the sign convention for shear stress as follows. Shear stress is defined positive if it is in the positive direction and it is acting on the positive phase. I'll explain what that means. So this is the shear stress tau xy, and my claim is that this tau xy is positive, right? So why is that so? Because first of all, there are four faces. This face is perpendicular to the positive x-axis. This face is perpendicular to the positive y-axis. This face is perpendicular to the negative x-axis, and this face is perpendicular to the negative y-axis. So in all, we have four faces. So we have two positive faces and two negative faces. So this is the positive x face because this face is perpendicular to the positive x-axis. This face is perpendicular to the positive y-axis. So we have two positive faces and two negative faces. Again, this face is negative because it is perpendicular to the negative x-axis, and this face is negative is perpendicular to the negative y-axis. Okay. So this shear stress tau xy, it is pointing in which direction? It is pointing in the positive y direction, and it is acting on which face? It is acting on the positive x face, right? So the stress is positive on positive. This stress, shear stress, is acting on a positive face in a positive direction. So then in that case, I would consider the sign of this shear stress as positive. If I consider this stress, this shear stress which is acting on the top face, if I consider this shear stress which is acting on the top face, right? So again, this shear stress is what? This is acting on the positive y face, and it is acting in the positive x direction. So again, this shear stress is positive. Again, if I consider this shear stress, so this shear stress is acting on the negative x face, and it is acting in the negative y direction, right? So again, you might remember that negative into negative is nothing but positive. So this shear stress is also positive, and similarly for this shear stress, it is acting in the negative uh, x direction, and it is acting on the negative y face. So this is again positive. So all the shear stresses are positive according to our sign convention, and uh, all the normal stresses as far as this case is concerned are positive. So let's move on to the next slide. Uh, so many times we have a case of a plane stress. What is a plane stress? We have seen the general state of stress on 3D block or a 3D element, right? So we have seen that in case we have a block like this, in case we have a block like this, then in that case we have one normal stress and two shear stresses on each and every face. Like we have a normal stress on this face and two shear stress on this face, and likewise on all the faces, right? So this is what, this is a general state of stress, general state of stress. Now many times it might happen that the normal stress on the z direction will be zero, and at the very same time the shear stress in the z direction and the shear stress will also be 0 on this face, right? So if the normal stress is 0 over here, normal stress is going to be 0 in the downward direction, and the shear stress is 0 on this face, then the shear stress has to be 0 on the corresponding opposite face, right? So this case will be reduced to this one, and this case is called as plane stress condition, right? Because the state of the stress is same in all the directions, right? You have sigma x on this face, you have sigma y on sigma x on this face, you have sigma y on this face, and you have sigma y on this face, and then you have shear stresses, right? Again, shear stress in z direction is 0, right? So tau xz is 0, tau yz is 0, right? So all the stresses in z direction are 0. So this case of plane stress can be simply represented by using this figure. Now we have to consider various loading conditions. The first loading condition is that we have a bar which is under uniaxial loading. Now what do I mean by uniaxial loading? What we have seen in the previous cases, this in this case, the first block, you can see the stresses were acting on all the three faces, right? So it was triaxial, or there are three axes, so it was a triaxial loading. In the second case, you can see that the stress is acting on two axes, right? Two mutually perpendicular axes. The stress is acting on two axes. So this is a case of biaxial loading. When stress on one of the axes is 0, then it converts to a case of biaxial loading. Bi means 2. So the last figure you can see is it's a case of biaxial loading. And then we have the simplest case, which is called as uniaxial loading. In case of a uniaxial loading, we have stress in only one axis, right? So this is the case of a uniaxial loading. So suppose that you have a bar which is uh, under the action of uniaxial loading, and you need to find out what are the various stresses inside the bar. So there are many ways you can do that. First of all, what you have to do is you have to cut the bar using an imaginary section. So suppose that I put a transverse cut over here. Transverse means perpendicular to the axis. So if I put a transverse cut over here, what I can see after cutting this bar over here, if I consider the left section of this bar. So over here, I'll consider the left section of this bar. So this is the left section of this bar. We have seen that on cutting any object which is under the action of forces and it is under equilibrium, there are some normal forces inside that, and there are some shear forces inside there. So this is one normal force and this is one shear force. And again, this normal force is what? Internal normal force and internal shear force. And the resultant of these two forces will be what? The resultant of these two forces will be P, because we have to keep this bar under equilibrium. So you can very easily see that if you sum all the forces, if you use equations of equilibrium over here, then you will find out that summation of forces in x direction is 0 and summation of forces in y direction is 0. So for this bar, for this case, you'll find out that if I do summation of forces in x direction is equal to 0, then this normal force N will be equal to P, and this shear force V will be equal to 0 if I do the summation of forces in y direction. Similarly, I can use a transverse cut. Transverse means a cut which is not perpendicular to the axis of the bar. So I've used non-transverse cut over here. So when I consider a section of this bar, like I'm considering the left section of this bar, so I can see that again there will be two forces, one normal force and one shear force. Normal to the surface and parallel to the surface. Parallel to the surface is shear force, and normal to the surface is normal force, which is denoted by N, and shear force is denoted by V. And the resultant of N and V should be equal to what? It should be equal to P, because again I have to keep the bar in equilibrium, right? Okay. So what we have to do is now we have to find out the relationship between what is the relationship between n and v and the angle of cut, right? So suppose that you have this bar, right, which was under uniaxial loading. This bar was under uniaxial loading, and suppose that the transverse area, right? So this area is what, AT. Now what you did is you put a transverse cut onto this bar and you exposed this area, and after exposing this area, you found out that there was a normal force and there was a shear force, right? So the normal force is called as N and the shear force is called as V. Also, if I find out this area, if I try to find out this inclined area, then I can find it out very easily from using trigonometric identities. This area will come out to be 80 upon the cosine of theta, right? So this is the transverse area 80, and this angle is theta. So this area will come out to be what, 80 upon cos of theta. So this area is what, transverse area divided by the cosine of theta. Okay, so I've got this area. I also know that the normal stresses on this area will be sigma. So if I multiply the normal stress with the area, so stress into area is equal to force. So I can calculate the normal force on this face by using this formula. Normal force will be equal to what? The normal stress into the area. Normal stress on this face is what? Sigma, and area is 80 by cos of theta or cosine of theta. So the normal force is going to be sigma into 80 upon cos of theta, right? And similarly, I can find out the shear force. Shear force can be found out by multiplying the shear stress with the area. So in this case, the shear stress is tau, right? So the shear stress is tau, and I can find out the shear stress by multiplying shear stress with area. So shear force is equal to what? Shear stress into area. It is again equal to tau into 80 upon cosine of theta. So I have found out both the forces, normal force and shear force, and their relationship with this angle theta. Now I know that this normal force is not independent of this angle theta, right? So if this angle will change, the normal force, internal normal, and the internal shear force will change, right? And there will be some angle theta for which this normal force will be maximum and the shear force will be maximum. And our objective is to find out that this happens for which angle. Okay. So in order to do that, what I can do is I can consider two directions. One is perpendicular to this plane, this perpendicular direction, and another is parallel to this plane. So I have considered these two directions, perpendicular and parallel. And what I'll do is I know that this body is in equilibrium, right? So I can use the equations of equilibrium for this body, and I can use equations of equilibrium for this body, and I can find out what is the relationship of P, N, and theta, or P, V, and theta, right? Because P is the external applied load, and N is what? The internal resisting force, and V is the internal shear force, right? So if I take the summation of forces in perpendicular direction or in parallel direction. So which are the various forces in this perpendicular direction? First is this normal force N, and also I can resolve this force P into this perpendicular direction. Now if this angle is theta, right? So this angle is theta. This angle will also be theta, and if I were to resolve it in the perpendicular direction, then it will come out to be what? P cosine of theta, right? And similarly, I can do the summation of forces in the parallel direction, and I can solve for tau and the normal stress and the shear stress. So the two formula comes out like this. Shear stress is equal to what? P by 80 into cosine square of theta, and tau comes out to be P by 280 into sine of 2 theta, right? So I've got the relationship of sigma with theta and tau with theta. Now, if I were to find out the angle for which my normal stress is maximum, then in that case, if you look at this formula, what will happen is, if uh, the value of this thing will depend upon the value of cos square theta, right? Because P is external applied load, which is constant, and AT is again the transverse area, which is constant. So if you have to maximize the value of this thing, you have to maximize the value of normal stress, then its value will depend upon the value of cos square theta. So we have to maximize the value of cos square theta, and in order to maximize the value of cos square theta, we'll have to maximize the value of cos theta. And we know that the maximum value of cos theta can be equal to 1, and in that case theta will have to be 0 degrees, right? So normal stress will be maximum when theta is equal to 0, and when is theta equal to 0? When you put a perpendicular or transverse cut, right? So in case of a transverse cut, your normal stress will be maximum. Also, if uh, if you put theta equal to 90, because for theta equal to 90, for theta equal to 0, the normal stress was maximum. If you put theta equal to 0 into this expression, which is the expression for shear stress, so you can see that if I put theta equal to 0 over here, then the shear stress will be equal to 0, right? And we know that this is true, this has to be true, because on this face there cannot be any shear stress, right? The value of V was 0. Next, if I have to find out what is the maximum value of shear stress, right? So in order to find out the maximum value of shear stress, again you have to maximize the value of sine to theta, and the value of sine to theta maximum can be equal to 1. In that case, 2 theta has to be 90 degree, or theta should be equal to 45 degree, right? So if theta is equal to 45 degrees, sine to theta will be equal to 1, and tau will be equal to P upon twice of 80. So the maximum value of shear stress can be equal to P upon twice 80, and for theta 45 degree. It means that if you cut this rod at an angle of 45 degree from the vertical, then in that case the shear stress on this plane will be maximum. But you can again note this one thing, that if you put theta equal to 45 degrees over here, right? Because theta equal to 45 degrees makes the shear stress as maximum. If you put the theta equal to 45 degree into this expression, then cos of 45 is 1 by root 2, and this will be equal to 1 by 2. So then in that case, sigma will turn out to be P by twice 80. Okay, so normal stress is not 0 when the shear stress is maximum, but shear stress is 0 when the normal stress is maximum. So this is one of the important takeaways from this part. Now, what is the necessity of doing this thing, right? So why do you need to do all those things? The thing is that if you have to predict the failure of any material, right? So you have to know what is the strength of the material under shear loading, and what is the strength of the material under normal loading, right? And suppose that your material suppose that you have a brittle material, and one case you have a brittle material and other case you have a ductile material, right? So ductile materials usually fail under shear stress, and brittle materials usually fail under normal stress. So you can see these two figures, and you can very accurately pin down which is a brittle material and which is a ductile material. So the figure shown over here, top figure shown over here, this figure is nothing but a brittle material, right? Because the plane of fracture is perpendicular, right? So it has failed under normal loading, and this material has failed under shear loading, because you can see the angle over here. So this angle is close to 45 degrees. So this is again failure under shear stress, right? Okay, so after considering stress transformations in uniaxial loading, we'll move on to biaxial loading. Actually, we have already covered this part in the class, so I'll not go into the details of how we have derived the expressions for stress transformation of biaxial loading. But I'd just like to reiterate that if this is your initial stress block, if this is your initial stress block, and if you rotate this stress block by some angle theta, then the stresses, initial stresses, which was sigma x dash on this x face, will change to sigma x on this face will change to sigma x dash on this face, right? The initial stress was sigma y onto this face. That stress will change to sigma y dash, and similarly tau xy will change to tau x dash y dash. Means if you change the orientation, the stresses will change. Like in case of uniaxial loading, when you were changing the orientation, you're changing the direction of the cut, the stresses onto the plane of the cut were changing, right? So we have already derived expressions for these stress transformations in the class, and we have called them stress transformation equations. So I'll just go to the stress transformation equations for case of biaxial loading. So these two equations represent what? They represent the stress transformation equations for biaxial loading, right? So if you rotate by some angle theta, then in that case you can find out the sigma x dash, right? So what was sigma x dash? Sigma x dash was nothing but the stress on this plane, or the rotated plane. So the formula for sigma x dash is nothing but sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cosine of 2 theta plus tau x by 2 sine of 2 theta. And similarly, the modified or the rotated shear stress is what? Minus sigma x minus sigma y by 2 sine of 2 theta plus tau x by 2 cosine of 2 theta. And again, I would like to reiterate that these equations assume that you have followed a certain sign convention, right? So if you decide to change the sign conventions, the sign and these equations will again change. Okay, so it's better to stick to one sign convention and follow them along. Also, if I were to calculate sigma y dash, then sigma y dash can simply be calculated with the help of formula of sigma x dash. What you have to do is you have to just change this theta to theta plus 90, because you can get the y dash phase if you rotate the x dash phase by 90 degrees, right? So you have to replace theta by theta plus 90, and if you do that, you'll find out that the formula for sigma y dash is simply this: sigma x plus sigma y over 2. There's a minus sign over here, there was a plus sign over here, there's a minus sign over here, minus sigma x minus sigma y over 2 cosine of 2 theta, and again there is a minus sign over here, tau x by into sine of 2 theta, right? So this is nothing but the stress on y dash phase. This is this stress on x dash phase and x dash y dash phase, shear stress on x dash y dash phase, right? One very important and one very interesting thing I would like to tell you is that uh, if you add sigma x dash and sigma y dash, what you will get is these two uh, these two will cancel out, like sigma x minus sigma over 2 into cosine of 2 theta, and minus sigma x minus sigma over 2 into cosine of 2 theta. This will cancel, and again this term will cancel. Tau x by sine of 2 theta minus tau x by sine of 2 theta will cancel, and you will find out that sigma x plus sigma x dash plus sigma y dash will be equal to what? Sigma x plus sigma y. So this is a very important result, that sigma x dash plus sigma y dash is equal to sigma x plus sigma y. Means the sum of the normal stresses in the initial orientation and the sum of the normal stresses after you have rotated is same. So this thing is something which is called as the stress invariant. There are some things which do not change with respect to the orientation, and this is one of those things. Like the sum of the normal forces, the sum of the normal stresses is a invariant. So the sum of the normal stresses do not change with respect to the angle theta, and this is a very important thing to remember, right? So we can see an example. We can solve an example. This is a stress block. This is a stress block, and you can see various stresses are shown onto this stress block. There's a stress of 80 megapascal. Now this stress will be negative because it is what this is, it is a compressive stress, compressive normal stress. So sigma x will be minus 80, sigma y will be plus 50 megapascal because it is tensile. And what about shear stress? So you can see that this shear stress is acting on the positive x phase, but it is acting in the negative y direction. So this shear stress will be negative according to our sign conventions, right? So tau xy will be equal to minus 25 degree. And what we have to do is we have to find out the shear stress if we rotate this element by 30-degree clockwise. And I might have forgotten to tell you that we consider theta positive if we rotate anti-clockwise and negative if we rotate clockwise. Right. So this is the rotated stress block. What you have done is rotated this stress block by an angle of minus 30 degree. And what you have to do is you have to find out what is the normal stress on this face CD. So you can find out the normal stress on this face CD by using this formula sigma x dash. So sigma x dash is what? Sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cosine of 2 theta plus tau xy into sine of 2 theta, right? So once you plug in all the numbers, you can find out what the normal stress is, right? What the normal stress on this face CD is. Similarly, you can find out what the shear stress on this face CD is by using the formula for tau x dash y dash, right? So tau x dash y dash is nothing but minus the formula for that is minus sigma x minus sigma y over 2 sine of 2 theta plus tau xy cos of 2 theta. So this comes out to be minus 68.8, right? Uh, So the normal stress was what? Minus 25.8, and the shear stress was what? Minus 68.8. So you can draw the normal stress and the shear stress in the rotated piece. So you have rotated this element, and now you can draw what are the normal stresses on this. So the normal stress was what? Minus 25 means it was compressive. So this is a compressive stress of minus 25.8, and again the shear stress was negative, right? So the shear stress will act in downward direction. Had it been positive, it would have acted in the upward direction, right? Okay, so we'll just take a small break, and we'll continue with we'll start with Mohr circle in the next section.